Today we discuss about knowledge representation basics. First, some definitions. An intelligent agent needs knowledge about the real world to make decisions and reason to act efficiently. Knowledge-based agents are those agents that have the capability of maintaining an internal state of knowledge, reason over that knowledge, update their knowledge based on observation, and take actions accordingly. These agents can represent the world using some formal representation and act intelligently. Basically, knowledge-based agents are composed of two main parts. We have the knowledge base and the inference engine. Now, the knowledge base is the key component of a knowledge-based agent. The knowledge base stores facts about the world. It is a mix of sentences defined using a knowledge representation language. On the other hand, the inference engine is a knowledge-based system engine used to infer new knowledge in the system. A knowledge-based agent must be able to do the following actions: to represent the state's actions and other aspects of the world, to incorporate new percepts, to update the internal representation of the world, to deduce the internal representation of the world, and to deduce appropriate actions. Now, humans claim that intelligence is achieved not by purely reflect mechanisms, but by the process of reasoning on internal representation of knowledge. In artificial intelligence, these techniques of intelligence are present in knowledge-based agents. A knowledge-based system is a system that uses artificial intelligence techniques to store and reason with knowledge. The knowledge is typically represented in the form of rules or facts, which can be used to draw conclusions or make decisions. One of the key benefits of a knowledge-based system is that it can help to automate the decision-making processes. For example, a knowledge-based system could be used to diagnose a medical condition by reasoning over a set of rules that describe the symptoms and possible causes of the condition. Another benefit of knowledge-based systems is that they can be used to explain their decisions to humans. This can be useful, for instance, in a custom service setting where a knowledge-based system can help a human agent understand why a particular decision was made. The knowledge-based systems are a type of artificial intelligence and have been used in a variety of applications, including medical diagnosis, expert systems, or decision support systems. What is a knowledge base? And why we use a knowledge base? Knowledge-based inference is required to update an agent's knowledge, learn from experiences, and take actions according to the knowledge. The inference means deriving new sentences from the existing ones. The inference-based system allows us to add new sentences to the knowledge base. A sentence is a proposition about the world. The inference system applies logical rules to the knowledge base to deduce new information. The inference system generates new facts so that an agent can update its knowledge base. Basically, an inference system can follow two approaches. We have on one hand forward chaining, and on the other hand we have backward chaining. A knowledge-based agent can be viewed at different levels. At the knowledge level, this is the first level of a knowledge-based agent. Here we specify what the agent knows and what the agent goals are. Next, we have the logical level. Here we specify how the knowledge is stored. At this level, the sentences are encoded in logical sentences by means of different logics. And then we have the implementation level. Here the agent performs actions based on the knowledge level and logical level. The three operations that are performed by a knowledge-based agent are the following. We have the tell operation. This operation tells to the knowledge base what it is perceived from the environment. Next, we have ask. This operation asks the knowledge base what action it should perform. And then we have perform actions, which performs the selected action. Here we have an example of a generic knowledge-based agent program. We have this operation of tell, ask, and tell. The knowledge-based agent takes percepts at input and returns an action as an output. Okay, so on one hand it takes percepts, it receives percepts, and then it returns actions. The agent maintains the knowledge base. The knowledge base initially has some background knowledge of the real world. The agent maintains a counter to indicate the time of the process. The counter is initialized with 0. Each time the program function is called, it performs three operations. First, it tells the knowledge base what it perceives. Then it asks the knowledge base what action it should take, and then it tells the knowledge base what action was executed. So basically we have three actions. We have make percept sentence, which generates a sentence based on the given percept and the given time. Then we have make action query, which generates a sentence to ask which action should be taken at the current time. And then we have make action sentence, which generates a sentence which asserts that the selected action was executed. So going back, okay, we have this persist knowledge base here below function. It's a knowledge base with facts and information about the environment. And then we have this tell, okay, which receives as parameters the knowledge base and make percept sentence, which generates a sentence based on the given percept and the given time. Next, we have the ask operation, okay, which receives as parameters the knowledge base and make action query, okay, which generates a sentence to ask which action should be taken at the current time. And then we have another theme which receives as parameters the knowledge base and make action sentence, which generates a sentence which asserts that the selected action was executed. And then we have this TA equals T plus 1. It means that we increment the time. Knowledge representation in artificial intelligence refers to encoding information about the world into formats that artificial intelligence systems can utilize to solve complex tasks. This process enables machines to reason, learn, and make decisions by structuring data in a way that mirrors human understanding. Knowledge representation can be defined as the following. It is the part of artificial intelligence concerned with artificial intelligent agents and how they are thinking. It is responsible for representing information about the real world so that a computer can understand and use this knowledge to solve complex real-world problems such as diagnosing a medical condition or communicating with humans in natural language. Or it describes how we can represent knowledge in artificial intelligence. The knowledge representation is not only about storing data, but also enables a machine to learn from experience so that it can behave intelligent, similar with a human. Here we have the knowledge representation in artificial intelligence. Okay, so artificial intelligence systems operate on data. However, raw data alone does not lead to intelligence. Artificial intelligence must transform data into structured knowledge. The knowledge representation achieves this by defining formats and methods for organizing information. With clear representation, artificial intelligence systems solve problems, make decisions, and learn from new experiences. The following information can be represented by an artificial intelligence system. Facts, these are truths about the real world. Objects, these are facts about objects. Events, actions that are occurring in the world. Performance, knowledge about how the agent should behave or act. Meta-knowledge, this is knowledge about the knowledge stored. And knowledge base, this is a group of sentences. Knowledge and intelligence and artificial intelligence share a symbiotic relationship. For instance, knowledge as a foundation. The knowledge provides facts, rules, and data. For instance, traffic laws for self-driving cars. Without it, intelligence lacks the raw material to act. Then we have intelligence as application. Intelligence applies knowledge to solve problems. For instance, a robot using physics principle to navigate there. Interdependence. Static knowledge becomes obsolete without adaptive intelligence. Conversely, intelligence without knowledge cannot reason or learn. For instance, an artificial intelligence with no medical database cannot diagnose diseases. Of course, it needs information about diseases. And synergy. Effective artificial intelligence systems merge robust knowledge bases, the what with reasoning algorithms, the how. For example, ChatGPT combines vast language data, the knowledge, with transformer models, the intelligence, to generate coherent text. Now, let's see some methods of knowledge representation. Logic-based methods use formal rules to model knowledge. These systems prioritize precision and are ideal for deterministic environments. Propositional logic represents logic as declarative statements, known as propositions, linked by logical operators such as and, or, not. For example, a proposition can be if it rains, proposition A, and ground is wet, proposition B, then the road is slippery, proposition C. While simple, it struggles to represent complex relationships. Often follows the format if condition, then conclusion. For instance, in a knowledge-based system, it could be if an object is red and round, then the object might be an apple. Next, another way of representing information or knowledge is first-order logic. This one extends propositional logic by introducing variables, quantifiers, and predicates. First-order logic can express statements like all humans are mortal. All humans, notice that we can represent with this sign. Uh, it supports nuanced reasoning but demands significant computation resources. These methods organize knowledge hierarchically or through networks, mimicking how humans categorize the information. Another way to represent information is by using semantic networks. They represent the knowledge as nodes or concepts and ages or relationships. For example, dog links to animal via an is-a connection. They simplify inheritance reasoning but lack formal semantics. Next, we have frames. They group related attributes into structured frames. For example, a vehicle frame may include slots such as wheels, engine type, or fuel. Frames are good for default reasoning, but they have difficulties, they struggle with exceptions. We also have ontologies. These define concepts, hierarchies, and relationships within a domain using standards such as Web Ontology Language, or simple define OL. Ontologies power semantic search engines and healthcare diagnostics by standardizing terminology. For example, e-commerce platforms use ontologies to classify products and enhance search accuracy. Here we have an example of an ontology. Probabilistic models. These systems handle uncertainty by assigning probabilities to outcomes. We have Bayesian networks that use directed graphs to model causal relationships. Each node represents a variable and edges denote conditional dependencies. For example, a Bayesian network can predict the likelihood of equipment failure based on maintenance history and usage. Another example of probabilistic models are Markov decision processes. They model sequential decision making in dynamic environments. For example, Markov decision processes help robotic systems navigate obstacles by evaluating potential actions and rewards. Another example, weather prediction systems combine historical data and sensor inputs using probabilistic models to forecast storms. We also have distributed representations. Modern artificial intelligence leverages neural networks to encode knowledge as numerical vectors, capturing latent patterns in data. Embeddings. They convert words, images, or entities into dense vectors. Word embeddings, like word2vec, map synonyms to nearby vectors, enabling semantic analysis. Knowledge graphs. They combine graph structures with embeddings to represent entities, for instance, people or places, and their relationships. An example is Google's knowledge graph, which enhances search results by linking related concepts. The artificial intelligence knowledge cycle represents the continuous process through which artificial intelligence systems acquire, process, utilize, and refine knowledge. This cycle ensures that artificial intelligence remains adaptive and improves in time. The artificial intelligence knowledge cycle is iterative. Artificial intelligence systems refine knowledge continuously, ensuring adaptability and long-term learning. This cycle forms the backbone of intelligent systems, enabling them to grow smarter over time. Knowledge acquisition. Artificial intelligence gathers data from various sources, including structured databases, unstructured text, images, or real-world interactions. The techniques such as machine learning, natural language processing, or computer vision enable this acquisition. Next, knowledge representation. Once acquired, knowledge must be structured for efficient storage and retrieval. Then following step in the knowledge cycle is knowledge processing and reasoning. Artificial intelligence applies logical inference, probabilistic models, and deep learning to process knowledge. These steps allows artificial intelligence to draw conclusions, for instance by deductive and inductive reasoning, to solve problems using heuristic search and optimization, and to adapt through reinforcement learning and experience. Next, we have knowledge utilization. Artificial intelligence applies knowledge to real-world tasks, including decision-making, predictions, and automation. Some examples include virtual assistants understanding user queries, artificial intelligence-powered recommendation systems suggesting content, or self-drive cars making real-time navigation decisions. Next, we have the knowledge refinement and learning. Here, artificial intelligence continuously updates its knowledge base through feedback loops. Techniques like reinforcement learning, supervised fine-tuning, and active learning help improve accuracy and adaptability. This ensures artificial intelligence evolves based on new data and experiences. Okay, and here we have the steps from the artificial intelligence knowledge cycle and how are they related one to each other. Types of knowledge in artificial intelligence. Artificial intelligence systems rely on different types of knowledge to function efficiently. Each type serves a specific role in reasoning, decision making, and problem solving. And now we'll see the primary types of knowledge used in artificial intelligence. Declarative knowledge or descriptive knowledge consists of facts and information about the world that artificial intelligence systems store and retrieve when needed. It represents what is known rather than how to do something. This type of knowledge is often stored in structured formats like databases, ontologies, or knowledge graphs. For example, a fact such as Paris, the capital of France, is declarative knowledge. Artificial intelligence applications like search engines and virtual assistants use this type of knowledge to answer factual queries and provide relevant information. Next, we have procedural knowledge or how-to knowledge. This defines the steps or methods required to perform specific tasks. It represents how to accomplish something rather than just stating a fact. For example, knowing how to solve a quadratic equation or how to drive a car falls under procedural knowledge. Artificial intelligence systems such as expert systems and robotics utilize procedural knowledge to execute tasks that require sequences of actions. This type of knowledge is often encoded in rule-based systems, decision trees, or machine learning models. Another type is meta-knowledge, or knowledge about knowledge. It refers to knowledge about how information is structured, used, and validated. It helps artificial intelligence determine the reliability, relevance, and applicability of knowledge in different scenarios. For example, an artificial intelligence system deciding whether a piece of medical advice comes from a trusted scientific source or a random blog post is using meta-knowledge. This type of knowledge is crucial in artificial intelligence models for filtering misinformation, optimizing learning strategies, or improving decision making. Heuristic knowledge or experience-based knowledge. Heuristic knowledge is derived from experience, intuition, and trial and error methods. It allows artificial intelligence systems to make educated guesses or approximate solutions when exact answers are difficult to compute. For example, a navigation system suggesting an alternate route based on past traffic patterns is applying heuristic knowledge. Artificial intelligence search algorithms such as A-star search or genetic algorithms leverage heuristics to optimize problem-solving processes, making decisions more efficient in real-world scenarios. Another type is common sense knowledge, which represents basic understanding about the world that humans acquire naturally, but it's challenging for artificial intelligence to learn. It includes facts like water is wet or if you drop something it will fall. Artificial intelligence systems often struggle with this type of knowledge because it requires contextual understanding beyond explicit programming. Researchers are integrating common sense reasoning into artificial intelligence using large-scale knowledge bases such as ConceptNet, which helps machines understand everyday logic and improve their interaction with humans. Domain-specific knowledge. This one focuses on specific fields such as medicine, finance, law, or engineering. It includes highly detailed and structured information relevant to a particular industry. For example, in the medical field, artificial intelligence-driven diagnostic systems rely on knowledge about symptoms, diseases, and treatments. Similarly, financial artificial intelligence models use economic indicators, risk assessments, and market trends. Expert systems and artificial intelligence models tailored for specific industries require domain-specific knowledge to provide accurate insights and predictions. Now, let's see some challenges in knowledge representation. While knowledge representation is fundamental to artificial intelligence, it comes with several challenges. Complexity is one of them. Representing all possible knowledge about a domain can be highly complex, requiring sophisticated methods to manage and process this information efficiently. Ambiguity and vagueness. Human language and concepts are often ambiguous or vague, making it difficult to create precise representations. Next, scalability. As the amount of knowledge grows, artificial intelligence systems may scale accordingly, which can be challenging both in terms of storage and processing power. Knowledge acquisition. Gathering and encoding information or knowledge into a machine-readable format is a significant hurdle, particularly in dynamic or specialized domains. In reasoning and inference, artificial intelligence systems must not only store knowledge but also use it to infer new information, make decisions, and solve problems. This requires sophisticated reasoning algorithms that can operate efficiently over large knowledge bases. Let's see now some application of knowledge representation in artificial intelligence. Knowledge representation is applied across various domains in artificial intelligence, enabling systems to perform tasks that require human-like understanding and reasoning. Some applications include expert systems. These systems use knowledge representation to provide advice or make decisions in specific domains such as medical diagnosis or financial planning. Natural language processing. Knowledge representation is used to understand and generate human language, and enabling applications like chatbots, translation systems, or sentiment analysis. Robotics. Robots use knowledge representation to navigate, interact with environments, and perform tasks autonomously. Semantic web. The semantic web relies on ontology and other knowledge representation techniques to enable machines to understand and process web content meaningfully. And cognitive computing systems like IBM's Watson use knowledge representation to process vast amounts of information, reason about it, and provide insights in fields like healthcare or research.